Good morning, everyone. We'll start, of course, the presentation with dual fuel engines, but certainly we need some topics from general marine engineering, marine engines. So I will start by mentioning the classification, not all the types of classification, but the classification of internal combustion engines, reciprocating internal combustion engines related to the fuel, to the cycle, and to the ignition type. We start by mentioning the fuel classification. So we have petrol engines, which operate by burning gasoline, natural gas, or LPG. And then we have diesel engines, which can burn marine gas oil, marine diesel oil, or heavy fuel oil. We have methanol, ethanol engines, and then dual fuel engines, and also engines that can burn petrol and ethanol mixtures and biodiesel. So a special category of these engines is the dual fuel engines. So then you may know that the engine is classified based on the cycle, so have two-stroke and four-stroke engines, and then based on the ignition type, we have the spark ignition engines and compressor ignition engines. So say that we can proceed to the classification of marine engines. So the marine engines, the engines used in onboard ships, can be slow speed engines or medium high speed engines, and then there are some advantages or functionalities of each category of engines. So for example, we know that the slow speed engines are used in merchant ships, large ships. They can provide large powers. They are the more efficient engines, thermal engines, obtaining efficiency up to 53%. They can have a cylinder diameter up to 1 meter or more than 1 meter. And they can burn very low quality fuels like heavy fuel oil. And of course, they can burn natural gas. Based on existing slow-speed engine types, the manufacturers have developed modified versions that can burn natural gas, as I will explain later. And of course, we have the medium high-speed engines or high-speed engines. Generally, high speed is considered an engine that has engine speed above 1000 RPM, and the medium speed is considered in the region from 400 to 1000 RPM. And these engines, of course, are used in ferry type ships or in cruise ships, but also in small merchant ships. I would say that this is the category of engine with the second most efficient engine, which means efficiency is up to 48%, and can be used when the height of engine room is limited, like in ferry ships. And of course, this kind of engine is used in all the diesel generator sets, which means that the engine drive electric generator for producing the engine, the electrical energy of the ship. So these three types can be seen, or the size of these three types can be seen in this slide. Starting from the left picture with a typical large two-stroke marine diesel engine. Of course, nowadays this engine model can be used also in dual fuel mode. And then we have in the middle a medium speed four-stroke engine. and then on the right we have a 4-stroke high-speed engine. Medium speed and high-speed engines are 4-stroke engines, whereas the large slow-speed engines are 2-stroke engines. So let's proceed by saying some engine room arrangements, some typical engine room arrangements. So this is the typical arrangement on board a merchant ship with one 2-stroke, usually 2-stroke large engine as prime mover, connected with the ship propeller using the propulsion system. In smaller ships, we can have one medium speed engine, but in this case, gearbox is needed between the engine and the propeller. Apart from the main engine, we have the auxiliary engines, diesel generators, usually 3, and of course, an auxiliary boiler depending on the ship type. So the question here is if the ship can operate by using, instead of heavy fuel oil or marine diesel oil or marine gas oil, by using natural gas or LNG, and then in which form the fuel can be stored on board. If we these are some more views of the floor plan and the first deck plan of the same ship. So we have the engine shafting system. In this case, we have a sub generator installed between the engine and the propeller. And then in the first deck, usually the typical installation is 3 diesel generator sets and medium speed or high-speed engines. And this is the case with a 4-stroke medium-speed engine, a gearbox, clutch and gearbox usually, shafting system and propeller. And for some ship types like ferries, more than one engines are required. So in this case, in this slide, 2 main engines are used for driving 2 different propellers. And then more than 2 engines can also be used. For example, in this case, which is a typical installation of a large ferry, 4 engines are used, and a couple of engines drives one propeller. Of course, the gearbox is needed in this case. And apart from the mechanical configurations mentioned or described previously, there are more modern configurations for diesel electric or dual fuel electric propulsions. So in this case, diesel generator sets are installed on board for producing the electrical power, and then electric motors are used for driving the ship propellers. Of course, each configuration has its own advantages and disadvantages, but the objective of this lecture, of today's lecture, is to see how we can, or if we can, replace the diesel engines in all the configurations with dual fuel engines, and which is the best type, if there is the best type of dual fuel engine that can be installed on board the ship. I will pass some slides providing information about the main parameters, operating parameters of internal combustion engines, because we will see these parameters in slides, later slides. So BMEP, braking effective pressure, is an important parameter and used almost universally for characterizing the engines, and by definition is the brake work divided by the displacement volume. Of course, we can define respective indicator mean effective pressure and friction mean effective pressure, but usually brake mean effective pressure is used. Then typical values for marine engines. For the large stroke engines, we have numbers up to 20, 19 to 20. And for large marine four-stroke engines, we have numbers for brake mean effective pressure up to 25 bars. And then we can also define the mechanical efficiency, which characterizes the losses, mechanical losses. And in this case, of course, we know that mechanical efficiency is the useful power over the given power. In the case of engine, we have the brake power, the rest of the brake power over indicated power. The larger the engine is, the larger is the mechanical efficiency. So lower speed, the slow speed engines exhibit the highest mechanical efficiency. Then other important operating parameters are the brake power of the engine, usually in kilowatts or in horsepower, which of course the brake power over the brake work delivered in one cycle. So this is the definition of brake power, and of course the torque, which characterizes the ability of the engine to produce work or the ability of the engine to overcome a load. And we know that torque is the brake work over the duration of the cycle, 720 degrees for four-stroke engines, 360 degrees for two-stroke engines. And of course, the very useful work of that connects brake power with torque. We know that brake power is torque times angular momentum, angular speed. Sorry. Some conversion numbers. 1 HP, 1 horsepower is equals to 0.7457 kilowatts. Just in case that kilowatt is typically used, but some cases horsepower is used as well. And then some other useful parameter is the air fuel ratio, with the mass of air over the mass of fuel, or the fuel air ratio, and then lambda, which is air fuel ratio over the stoichiometric air fuel ratio. Stoichiometric air fuel ratio is a property of fuel, and depends on the composition of the fuel. And the reciprocal of lambda is called phi, which is the fuel air equivalence ratio. In dual fuel engines, lambda is an important parameter, and we'll see later on in some diagrams that there is a lambda window, an operating window in terms of lambda that the engine needs to operate, and the manufacturer has to ensure that the engine will operate in this operating window. So it's a very important parameter. And then brake specific fuel consumption, which means grams of fuel per kilowatt hour of energy, or per HP an hour. Usually grams per kilowatt hour is used. An alternative to brake specific fuel consumption is the brake energy consumption. We see some graphs in the later slide, in below slides, that brake energy consumption is used instead of brake specific fuel consumption. In any case, brake specific fuel consumption characterizes the efficiency of the engine. Actually, is a reciprocal of efficiency, as we'll see in the next slides. So, yeah, efficiency is defined as what the engine provides over what the engine receives. And we have the brake efficiency, which is actually the brake power over the thermal power provided by the fuel. We have indicated efficiency, we have the combustion efficiency, and as I said just earlier, the brake space fuel consumption is the reciprocal of brake efficiency, or the brake efficiency reciprocal of brake space fuel consumption. So if we know the one, we can calculate the other, and this equation here connects the brake efficiency of the engine with the brake space fuel consumption. And an important parameter which also property of the fuel and used in this equation is lower heating value. And that means if the lower heating value of a fuel is greater than the lower heating value of another fuel, then lower or less amount of fuel is required. So we can use this equation to calculate by given the brake space fuel consumption, we can use this equation to calculate the efficiency and vice versa. So the last slide related to the engine operating parameters is defines the volumetric efficiency, which actually is efficiency that is a parameter that is used to characterize the gas exchange process, and of course this is related to lambda as well. So next, what we need to remember when we're trying to read or to find out the efficiency of the engine is that we need to remember that provide energy by injecting fuel, and then based on the processes involved in the engine, the engine provides power or brake power, useful power, and actually we need to define the energy balance in order to know where this energy, the energy of fuel, is distributed. And the energy of fuel is distributed to brake power. We have a coolant needed for keeping the temperature of metallic parts at the normal level. We have a part of heat transferred to the environment, and also we have a part of energy transmitted to the ambient by the exhaust gas. So, in conclusion, the energy provided or the power provided by the fuel will be equal to the power, the brake power of the engine, plus the coolant power, plus the exhaust gas power, plus the radiation power or miscellaneous power, which cannot be measured. And we need to always to have in mind this equation, because this can explain actually some of the processes occurring inside the engine. The objective, one of the objectives for using dual fuel engines, and of course replacing the diesel oil with natural gas, is to increase the brake power of the engine for the same fuel power, and then we will discuss this later on. Also, we can define some percentages apart from the energy brake efficiency or brake efficiency of the engine. We have the exhaust gas loss percentage, the cooling power percentage, and the miscellaneous power percentage. Typical values for the marine engines generally The brake efficiency for large engines are close to 50% or a bit above 50%. 25% we expect for the energy exhaust gas losses, and then 20 to 22% or 24% expected for the cooling power, and less than 1% expected for the radiation or miscellaneous power. And then, so one of the drivers introducing dual fuel engines or introducing natural gas as fuel is to increase the efficiency. The other driver is the emission regulations. Just to remind you, of course, the other lecturers should have given these figures. As far as the NOx is concerned, we have 3 levels: Tier 1, Tier 2, Tier 3. Currently, we're in Tier 2, and from 2021 onwards, there is a large possibility that Tier 3 will come into effect, although it was to come into effect from January 2016, but this postponed for some years. So we need to have in mind that this will result in a large pressure for the engine manufacturers, and then we need to know that there are limits also for the sulfur content of the fuel. Actually, the limit was introduced to decrease the SOx emissions. So also we need to know that there are two areas. There are exhaust control areas called as ECAs, where the permitted sulfur content is very low, 0.1% from 2015 onwards. And in the other areas, up to now, the permitted sulfur content is 3.5%, but there will be a huge reduction to 0.5% from 2020. So thus, these two factors, emission limits for NOx and SOx emissions, increase the pressure towards alternative fuels or fuels with low sulfur content and fuels that can reduce emissions. And one of the ways that can reduce emissions is by introducing a dual fuel engine. So we can see here the various methods for reducing or for complying with Tier 3 and for complying also with Tier 2. High pressure or two-stage turbocharging can increase NOx by 40%. Low NOx combustion tuning can decrease the NOx by 10%. EGR system can decrease the NOx by 60%. Humidification can provide a benefit of 40%. Emulsion with water can provide a reduction at 25%. Direct water injection can provide a reduction of 50%. Catalytic selective catalytic reduction can decrease the NOx by 80%. And fuel conversion, which means operation of the engine by using natural gas as the dual fuel mode, can decrease NOx by 45%, but we need to remember that these are not absolute values, and the reduction depends on the type of engine, because as I will describe later, there are various types of dual fuel engines. So this 85% is valid, but for one specific engine type. And then the use of LNG, which actually is the use of natural gas. LNG is a form of storing the natural gas on board ships. can provide a reduction of CO2 by 30% and an increase of efficiency, because efficiency of the engine and brakes with fuel consumption is proportional to CO2 emissions. As I mentioned, there is a reduction of NOx by 85%. And as far as LNG, which means liquefied natural gas that does not contain sulfur or contain only a tiny amount of sulfur, then it means that SOx can be eliminated. So that actually explains why LNG or natural gas will has been started using on board ships, and of course there is an initiative for continuing this trend. Another driver is the natural gas LNG price, which is 40% less than heavy fuel oil price. But of course that depends. The price always depends on the demand of the fuel and the offer of the fuel. So we don't know if this will remain, but given the current trends, we know that LNG fuel is an attractive alternative. Okay, so trying to explain why we have emissions on the exhaust gas and which kind of emissions will be expected, we need to see the composition of its fuel. And we know that hydrocarbon fuels are basically involve carbon and hydrogen, but also other constituents like sulfur or nitrogen and oxygen or water and ash. And generally, in a diesel fuel, we expect 87% of carbon, 13% or 12% of sulfur, and 1% of 13% of hydrogen, 1% of sulfur. Of course, depending on the fuel, if it's low sulfur or normal fuel. And if we see the LNG composition, of course, LNG composition varies depending on the geographical area that this is natural gas is produced. But the main constituent of LNG is methane. And actually, methane composition varies from 87 to 95%. And then, apart from methane, we will find in LNG ethane and propane, butane, and nitrogen. During the liquefaction process, nitrogen is totally removed, because the liquefaction temperature is different in natural gas and nitrogen. So LNG does not contain nitrogen or contain only a tiny small amount of nitrogen. So trying to explain the reduction of CO2 emissions, we need to consider the combustion equation, and I have some. I will go in this in the latest, but let's see first which are the main emissions expected from combustion of hydrocarbon. So we have the hydrocarbon on one hand, and then we have the air provided to combustion on the other hand, and the combustion will give products CO2, carbon dioxide, and carbon monoxide, and water vapor, and SO2, and probably some amount will be converted at SO3, and then nitrogen, and unburned hydrogen, and as mentioned, and hydrocarbons, unburned hydrocarbons like methane or ethane, and then the process also will give nitrogen monoxide or nitrogen dioxide and particulate matter, or unburned carbon. And of course, we know that the emissions are say, are dangerous and have consequences to the environment and to living organisms. And of course, there is a trend to reduce emissions. So up to now for shipping, the main initiatives is to reduce NOx, which means monoxide of nitrogen monoxide, dioxide of nitrogen, nitrogen dioxide, and SOx, which means SO2, SO3, and CO2, and the latter actually was initiated by the introduction of EEDI, the Energy Efficiency Design Index, and the introduction of EOI, Energy Efficiency Operational Index, which actually are both related to CO2, carbon dioxide emissions. So now the pressure is to reduce CO2 and NOx, but there is a paradox here, because if we see this equation and if we consider the processes occurring in diesel engine, the trends are opposite. So, for example, trying to increase CO2, you can decrease NOx. Of course, SOx are only related to the content of sulfur in the fuel. But the trend between CO2 and NOx is opposite. For example, as I said, trying to reduce NOx as required by Tier 3, the CO2 emissions will be increased. And if you try to increase CO2, then you increase NOx. So it needs actually optimization and careful attention, because it's not an easy task to reduce both emitters. So CO2, as we discussed earlier, depends on the fuel content in carbon. So you can see here the emission factor of usually provided by IMO or other sources in kilograms of CO2 per kilogram of fuel. Depends on the carbon composition of the fuel. And if you remember from a previous slide, for diesel oil we expect 87% or 0.87. We haven't discussed which is this C for the case of natural gas, or for a case of gaseous fuel like methane, discussed in a way. And the CO2 emissions, or CO2 conversion factor, of course depends, there is a typo here, this is S, on the sulfur content. So by reducing the sulfur content, then you can directly reduce SOx emissions. Yeah. So the question gives, or the emission factor, kilograms of SO2 per kilogram of fuel, is equal to, or it's almost equal to 2 times S. So a 3% sulfur content gives 0.003 kilograms of SO2 per kilogram of fuel. And if this is 0.1%, then of course this will be reduced. So for CO2 emissions, we need to consider the carbon content of the fuel. For the case of methane, this C is 75% or 0.5, which means that the fuel, the methane, contains 75% of carbon and 25% of hydrogen. And that, thus, this change of fuel reduces the produced CO2 per kilogram or per amount of burnt fuel. So this is why, or the factor that reduces CO2. Now, let's see. So all these slides explain, all this information explains why there is um, a trend for introducing dual fuel engines. But as I mentioned earlier, there are many types of dual fuel engines. So let's see the basic categories, and of course then we will discuss what happens in two-stroke engines, four-stroke engines. The basic types of dual fuel engines are three. So we have the diesel gas concept, usually GD, diesel gas concept. So in this case, in the diesel gas concept, the engine operates in diesel mode, but instead of only diesel, blue jet denotes diesel fuel. The green jet denotes natural gas fuel. In this case, natural gas is injected at the same time with diesel fuel. So we have a combustion of natural gas and diesel fuel. So this is the diesel gas diesel concept, GD. And then we have the spark ignited concept. What happens here? The fuel is injected in gaseous form, so we have a natural gas injected either in port injection or directly in the combustion chamber, and then the combustion starts by a spark plug. So there is a spark plug installed in the engine head, cylinder head, and by initiating a spark that provides the initiative for start of combustion. And then there is the dual fuel engine concept, and in this case we have, of course, two fuels. We have the natural gas fuel, the gaseous fuel injected either in the port or directly in the combustion chamber. We'll discuss the difference later. And in this case, we need a pilot fuel, usually diesel oil, that is injected within the combustion chamber, and of course provides the initiation of combustion. So the concept, as described, as far as the combustion is concerned, we have two concepts actually. We have the lean burn or premixed combustion. So in this case, the fuel, the gaseous fuel, is injected in the port or in the cylinder, as I will explain later on. You can understand that there are many types of dual fuel engine. We need to know which one has to be selected for a specific application. We need to know the pros and cons of each one. So let's start now with the combustion types. So have, as I said, the lean burn or premixed combustion. In this case, in the combustion chamber and close to the end of compression process, we have a mixture of gas, natural gas and air. So the pilot fuel is injected there, and we have actually a jet developed, which can be developed within the combustion chamber. And then when the conditions will be appropriate, the combustion will be initiated, and that will give that will provide the initiative for the combustion of the mixture, the gas air mixture contained in the combustion chamber. So this is the lean burn combustion or premixed combustion. And then in the gas ignition or gas diesel engines, we have the simultaneously injection of two jets of two fuels. So we have the pilot fuel and the gas fuel. So in this case, as I will present in a later slide, combustion happens actually in parallel. So there is initiation of combustion from the pilot fuel, and then combustion is transferred to the gas jet. I will remind you that in order to have combustion, we need to have a mixture of air and fuel. So the fuel, either gas or liquid, will not start burning unless it will mix with air. So the process is more complex. So we have the development of the spray, we have the break of the spray small particles, we have the mixing outside the surface of the spray of fuel particles with air, and somewhere, we don't know where because this process is chaotic, somewhere combustion will start. When combustion will start, the whole process will be accelerated because energy will be provided in the mixture, thus increasing the temperature of the mixture, and of course this will allow for the burning of the full amount or almost full amount of fuel. This type of combustion is called diffusive combustion. We have premixed combustion and diffusive combustion, two different types of combustion. So let's discuss a little bit the advantages or disadvantages of each one of the mentioned types. So as I said, we have the gas diesel engine, we have the dual fuel engine and spark ignited engine. Just to mention that in the case of dual fuel engine, the pilot fuel percentage is only up to, let's say, 3%. So as you can see here from this orange strip, in dual fuel engines, the pilot fuel, the liquid fuel, is from 1 to 3% of the total fuel amount. In the case of gas diesel engines, you can see that the pilot fuel can be greater. So in that case, and of course in gas spark ignited case, we have only gaseous fuel, natural gas. So which are the advantages or disadvantages of all the functionalities of different types? For the case of gas diesel engine, the combustion is not NOx sensitive. You know what is NOx, I expect, or not. So knock or knocking is abnormal combustion. Generally, not generally, always we need to avoid knock because it actually increases the pressure, so it introduces vibration in the combustion chamber, and is very dangerous. The engine can be, or the engine components can be destroyed. In order to avoid knock, the engine or the combustion, the fuel injection should be carefully selected, and of course we need to inject the pilot fuel before the uncontrollable start of combustion. So in the case of gas diesel engines, these engines are not sensitive to knock. Another important parameter of the fuel is the methane number, and methane number is not an issue in this case. As I mentioned earlier, LNG, various LNG type contain various numbers or various amounts of methane, from 87% to 95%, and this characterizes the methane number of the fuel. The hydrocarbons and CO are low. Why? Any explanation of that? So why, in the case of gas diesel engines, the hydrocarbons and CO, carbon monoxide, are low? Because the pressure is high. So the engine operates in diesel mode, and you know that when the engine operates in diesel mode, the pressure, compression pressure and then combustion pressure is high. And when the pressure is high, this is suppresses unburned hydrocarbons and generation of or production of carbon monoxide. But the disadvantage of this high pressure and of course high temperature is that NOx is high. So CO is high, the efficiency of engine for CO2 is high, efficiency of engine is high, the CO2 is low, but NOx is high, and therefore this type of engines does not justify tier 3 level. And this is an issue, we'll discuss later how this can be taken into account. This is an issue for this type of engine because the engine can comply with SOx limits, but the engine cannot comply with NOx limits. And then it needs another technology, usually EGR, exhaust gas recirculation, or selective catalytic reduction, in order for the engine to comply with the set limits by IMO. So that's the first category. Next category is dual fuel engine. In this case, we have, as I mentioned, we have premixed combustion. So that means that the fuel will be injected in the port. So here we have the gaseous fuel will be injected in the port. So we have the gas, a natural gas injector in the port. And then at the end of the compression process, we'll have a mixture of natural gas in there. This is the pilot injector. Pilot fuel is used. The pilot fuel, liquid fuel, will be injected in the combustion chamber, as explained in the previous slide, and that will initiate combustion. So, which are the advantages of this concept? It justifies or it complies with the tier 3 NOx level because in this case the pressure is lower, so the compression pressure is lower. I can mention some compression ratio values. For example, I know that dual fuel engine operates at 10 to 11 compression ratio compared with a diesel engine that operates in 14 or 15 or higher, depends on the turbocharging level. So NOx is low due to the lower pressure level. Higher ignition energy than spark plug. Of course, the pilot fuel can provide the energy required for the start of combustion. High efficiency in gas mode, but is fuel sensitive, which means that the methane number plays an important role in the operation of the engine. So it needs methane number than 70, above 70. It is NOx sensitive, which means that it can operate in a lambda window from the lambda value should be from 1.8, 1.9 to 2.2, usually in this region, as I will explain later. And hydrocarbons, the unburned hydrocarbons and CO are high. Why? Because as I mentioned in the previous category, as the pressure is high, hydrocarbons are low, but in this case the combustion pressure is lower, so that increases unburned hydrocarbons and carbon monoxide in this type of engine. And then the last category, which means the gas ignited engines, a spark plug should be installed in a cylinder head. Of course, in this case, we are talking about premixed combustion. So the gaseous fuel, natural gas injected again in the port, and then we have injection, compression. The end of the compression, a premixed mixture of natural gas and fuel exists within the combustion chamber, and then a spark can initiate the combustion. So again, as far as the engine operates at auto combustion, which means lower pressures, the NOx, NOx are low, which means that the engine can comply with Tier 3 levels. There are no additional fuel, but this can be a disadvantage when we are talking about when we take into account redundancy required in onboard the ship. High efficiency can be obtained, and this high efficiency can be explained from the different carbon-hydrogen ratio of natural gas. Of course, again, as it's premixed combustion, the engine is fuel sensitive at NOx, so a lambda operating window is required. Again, methane number should be, methane number affects the engine operation. Hydrocarbons and carbon monoxide is high. The engine can accept low load or can operate at low load, but as I mentioned, there is no backup fuel, there is no second fuel that can be used in case of an emergency or cases that the engine can an engine deficiency can be observed. So, by saying that, let's see some more details of the premixed combustion engine. So the process is that we have the natural gas injection in the port by using an injector. During the induction process, inlet valve is open, piston moves downwards, so that initiates a mixing process between the natural gas and the air. And at the end of the combustion, of course, we have a mixture, a perfect mixture of natural gas and air. So the pilot fuel is injected, and that initiates the combustion. And of course, we have a premixed combustion in this case. And let's see in this frames what happens or how combustion starts. So we have the pilot spray, the development of pilot spray. As I mentioned, the spray breaks in small drops, and the small drops break smaller drops, and there's a mixing between the drops and the mixture of gas and air contained in the combustion chamber. And somehow and somewhere, the pilot spray will be ignited, and then as there is, so this is the area that we have a start of have the ignition, and then this will provide the energy to burn the whole mixture contained in the combustion chamber. So you can see that after the ignition, the combustion process quite fast, and the whole mixture can be burnt within 3 or 5 degrees of Fahrenheit. So very quick process. Where or in which, as I mentioned, we have 4-stroke engines, 2-stroke engines. And 2-stroke engines are used as prime movers, and 4-stroke engines are used as diesel generators, but also in ferry type ships, in cruise ships, or in small merchant ships. 4-stroke engines can be used as prime movers as well. So in which type of engines dual fuel premixed combustion can be used? 2-stroke or 4-stroke?
For premixed, 4-stroke.
In both. Actually, in both, as I will explain. So, yes, indeed, the manufacturer started converting the 2-stroke, the 4-stroke engines, the medium-speed engines, dual fuel engines using the premixed combustion concept. But last year or recently, Wärtsilä Sulzer actually introduced this concept to 2-stroke engines. The only difference, we say that the natural gas injected in the port, And this happens in four-stroke dual fuel engines. For the two-stroke engines, the gas is ejected within the combustion chamber when the piston is at the low part of the stroke. So during the compression, I think 5 injectors inject the gas to within the combustion chamber, and of course during compression there is a mixing of this injected gas and the air content in the combustion chamber. So at the end of compression process, pilot fuel is injected, and this initiates combustion or facilitates the combustion at the premixed concept also in the two-stroke engines. Which is the advantage? We discussed about the advantages and disadvantages of premixed combustion. Certainly we expect low NOx, and of course this type of engine complies with Type 3. But which is the disadvantage we expect from this concept? Take into account that this engine needs to operate in lower pressure levels.
Higher carbon.
The disadvantage actually is that for the same displacement volume, the power produced by the engine is lower. So we can see here what Wärtsilä gives from a diesel engine, the same size, same number of cylinders, and the dual fuel engine of premixed, two-stroke premixed concept, and you can see that the power obtained at let's say MCR cooling is reduced when using a dual fuel concept. And this leads to the requirement for increased number of cylinders. So usually in LNG carriers, because this concept or this type of engines started being installed in LNG carriers, usually one more cylinder is required to cover the power that can be delivered by respective diesel engine. Of course, the advantage of the concept is the low NOx, low SOx as far as natural gas does not contain sulfur at all, high efficiency, low pressure of the natural gas. The natural gas is injected in a pressure of 5 to 7 bars, so I think the pressure of the natural gas piping system should be around 8 or 10 bars or 12, something like that in this level. We keep this value because we need to discuss it in the case of the other concept, the gas injection, direct gas injection used by MAN, diesel and turbo. The engine is prone to knocking, so also lambda operating window is required. Lambda should be around 2, as we discussed earlier. And of course, there is an issue, or should be an issue, with hydrocarbon emissions due to the lower pressure level. But the fact is that Wärtsilä released this concept, released these two-stroke engine models, and this engine also exists in the market. Yes?
Is it possible to retrofit an existing two-stroke diesel engine to this type of engine?
I'm not sure.
Because you have to open.
Yes, but I'm not sure. I haven't heard the retrofit because in this, as I said, this type of engines, the primary market is LNG carriers. I don't know actually. So, but Wärtsilä should advise on that if it's possible or not, because the problem is that for each conversion, a full conversion package is needed. Even in the case of a four-stroke engine, in order to be converted in a dual fuel engine, a four-stroke diesel engine, a full conversion package is needed that which contains changing of engine components, injectors, the piping system, the feeding system, and so on and so forth. So it's not just you have the fuel on board the ship and that's all. So you need, of course, an extensive conversion.
Yes, but in this case you have to open holes on the block
Yes.
of the engine, and I suppose that is something complicated.
Anyway, but I think Wärtsilä, if you go to the site of Wärtsilä, you can find more information about that. So, the alternative or the competitor in two-stroke engines is the gas ignition type engines from MN diesel turbo. So in this case, of course, the two-stroke engine is the most common type of engine installed on board large ships. You know that as prime mover, and heavy fuel oil is needed. Actually, this type of engine, two-stroke engine, can burn every type of fuel independently of the quality. And of course, cheap heavy fuel oil is used. So the concept here is that natural gas can be injected by a separate injector. So you can see here the gas injection, the pilot injection. The two fuels are injected simultaneously, and we have a diffusive combustion of pilot fuel and gas fuel at the same time. So the engine is called the GI. So it's the typical engine code plus GI, gas ignited or gas injection, if I remember correct. In this case, pilot fuel injector and natural gas injector, of course, is required. And then, in this case, you can see here that we have the gas fuel and the pilot fuel. So certainly the combustion will be initiated by the pilot fuel. So we have again development of the jet, braking. I mean about the liquid fuel, the pilot fuel. It's a liquid fuel, injected in liquid form. So the spray is developed. It breaks in small drops, and the small drops break in smaller drops, and there's a mixing process around the periphery of the jet. And when the mixture will be found in appropriate conditions, combustion will start. So you can see here various frames for this type of process, which of course is more complex. It's a complex, if you consider that combustion of a liquid fuel is complex, then the combustion of a gaseous fuel and a liquid fuel is more complex certainly, but at the end of the combustion, the whole amount of, or almost whole amount of both fuels, pilot and gas, are burnt. And of course, in this case, natural gas can replace the part of the diesel fuel, or not the part, the largest part of the diesel fuel. As far as so we need to know that for the pilot fuel, only 1 to 3% of the total amount of fuel is required. So this is the case. Which are the advantages, which are the disadvantages of this engine? So advantages are that the gas can replace perfectly the liquid fuel. There's no need for installing another cylinder. The engine produces the rated power, even in dual fuel mode. The disadvantages include NOx limit, the NOx emissions, which are high. Of course, are reduced related to the diesel mode, but are still high. So I think the reduction of the reductions are above about 40%. But if you remember from my first slides, 85 or 90% reduction is required. And in this case, the disadvantage is that in order to comply with Type 3, another technology for reducing emissions, NOx emissions, is required. For example, SCR, selective catalytic reduction, or EGR. And in this case, here we have also an example of what happens with EGR and why, of course, the combustion is a little bit different. So we have a standard gas injection, and then we have a gas injection with EGR. You know what is EGR, correct? So the EGR concept works that we take exhaust gas from the exhaust receiver of the engine, we clean it, we cool it, and then we provide this exhaust gas to the scavenging receiver. And by doing that, the oxygen level is decreased. So instead of having an oxygen of 21%, this is the oxygen level condensed there, 21%. Then with EGR we can reduce oxygen level, and in this case, in these frames here, we have a case with oxygen level 17% instead of 21. And this reduces NOx by which way? So this reduces NOx because the combustion is lower. So you can see that what happens is the heat release rate. The red line and the black line is the heat release rate, cumulative heat release from gas ignition concept, and then by using AGR, you can see that combustion delays. So the heat is released more slowly than the case of the normal engine operation. So that reduces the maximum pressure and reduces the maximum temperature, or changes the temperature. And of course, this affects NOx. So you can see here that NOx standard in ppm, parts per million. In the standard, in the diesel engine is 500 ppm for this specific case. For the standard gas ignition, the NOx was reduced to 300 ppm, and by using EGR, NOx further reduced down to 44 ppm. So that actually reduces misgas.
Does this concept affects the efficiency of the engine?
No, it affects the efficiency as far as for operating EGR, the EGR system, energy needs to be consumed. Yeah, it affects slightly. Certainly, it affects hydrocarbon emissions and carbon monoxide. So, as I mentioned before, we have two different trends. Trying to increase efficiency and reduce CO2 will increase NOx. If we need to reduce NOx, then we will increase CO2 and decrease efficiency. So there are opposing trends, and yes, certainly there is some influence on of the efficiency. But if I remember correctly, it's only 1 gram per kilowatt hour, something like that. It's not large, according to the manufacturers. So that's the case with the two-stroke gas ignition engines. What we have here, so these are figures provided by Wärtsilä, and this is brake specific energy consumption. Is actually proportional to brake specific fuel consumption, kilojoule per kilowatt hour. So what we have here, we have the engine, this is for constant speed engines, the brake specific energy consumption for various types, for inline engines and for V engines. And then what we have here, we have for, so these constant engines are used in diesel generators or generator sets. Now we have dual fuel generator sets. And also in the case of dual fuel electric propulsion. And variable speed engines are used in case of mechanical propulsion with propellers. So in this case, this is the speed versus load. And what we have here is the brake specific energy consumption for inline engines and for V engines. Of course, the efficiency is a little bit different. Depends on turbocharging system, depends on the number of cylinders, and also we expect different efficiency between the diesel mode and the dual fuel mode, as far as the operating conditions completely change. But certainly, the outcome is that dual fuel engines are quite efficient engines. Operating window. I mentioned many times knocking issue, and which is only valid for premixed combustion type. And then we have a region, what we have here. So we have the vertical axis BMF, braking effective pressure, which is proportional to torque, and characterize engine load. And also in the horizontal axis we have lambda, excess air fuel over air fuel stoichiometric. And then you can see the yellow area, which is the knocking area. So the engine cannot operate in this area. You can also see with this orange area that there is an area with misfiring, which means problems in or issues with the combustion. So actually the engine can only operate safely in this blue area. And if we see the lambda values, 2, as I mentioned, that full load actually is very small, from 2 to 2.2. But in lower loads, you can see that the window is a little bit larger, from 1.8 to 2.2. So we need to know, or we need to remember that the premixed combustion engines, which means all the 4-stroke dual fuel engines and 2-stroke Wärtsilä engine, can operate in this lambda window. And this is the curve of BMF. This is the efficiency of the engine. NOx is very low. You can see that NOx in this lambda value or lambda window is very low. And carbon monoxide, which is also is not at its minimum value, but it's a little bit higher than the minimum value. But the important thing to remember is that the engine can operate, or this type of engine can operate in this lambda window. And this is important. Why? Because the turbocharging system, which provides the air to the engine cylinder, needs to be suitably selected for to accommodate the engine operation at dual fuel mode and at diesel mode. So there are two different concepts, diesel mode and dual fuel mode, and of course compromise needs to be made there as far as the turbocharging system is concerned. So another important thing to remember is that the engine should be always monitored, because knocking can provide or can cause severe problems in the engine. And in this case, what is needed is accelerometers and pressure sensors, and of course the pressure diagrams are recorded and analyzed. And of course, knocking affects, as I said, knocking affects the pressure level, pressure variation, and of course, pressure change or pressure variation produces vibrations and can be detected by measuring acceleration. So in this case, the pressure and acceleration, the pressure inside the cylinder and acceleration in various parts of the engine are recorded, so that ensuring that the engine operation, I think this is the case of constant speed, this is the case of variable speed, are according to the required, according to the specification within this lambda window. So this is very important. So this is another possibly obligation or an additional requirement for installing a sensory monitoring the engine, which is not which does not exist for the case of diesel engine. Diesel engine, of course, the operation is monitored, but acceleration measurement is not needed, and the pressure diagram is measured only from time to time, not continuously. Methane emissions, a very important issue for dual fuel engines. Why? Because there are these crevices, and we expect that you can understand which components of the engine are shown. You have here the piston of the engine, the liner, and the piston ring. And of course, there is a crevice, there is a gap between the piston and the liner, and in all these gaps, mixture of natural gas and air is trapped. And actually, this is a source of this is a source of burnt hydrocarbons, because combustion cannot occur in these crevices, and as a result, hydrocarbon levels increase. But actually, the manufacturers, when started introducing the concept of, when started working on this concept of dual fuel engines, modified the design. So they removed the ring at a higher level of the piston skirt area, and that decreased the volume of crevices, decreased the gap, so that actually resulted in acceptable level of burnt hydrocarbons. And of course, the basic constituent contained here is methane. As far as LNG contains 90% of methane, or close to 90% of methane. That means that the basic problem with burnt hydrocarbons are in terms of methane emissions, but as we can see here, this is no. I don't have methane emissions here, but I'm not remember if I have some. No, the methane emissions with kept in the levels of let's say 4 grams per kilowatt hour. So up to now it's quite acceptable, but certainly some changes in design is the initial design of diesel engines are required. So if we compare the overall let's say performance and emissions of dual fuel engines, actually I took two figures concerning two different engines. So gas diesel engine, which means injection of gas and pilot fuel directly into combustion chamber, and dual fuel engine, premium combustor. So we can see that there is okay, diesel mode is represented by black bars. Orange bars represent gas mode or dual fuel mode. So we have a decrease of CO2, which is attributed to the different carbon ratio between diesel or liquid fuel and gas fuel. This change is 12% for the case of gas diesel engine, and I think it's 30% for dual fuel engine. We have a small increase here. We have a 20%. No, it's 22%, 25%. Let's say it decrease 10 weeks. A huge decrease of NOx for the case of dual fuel engine. A large decrease of SOx, almost elimination of NOx in dual fuel engine. I think that depends on the amount of pilot fuel. If the pilot fuel is low sulfur fuel, then the decrease will be different. And then, as far as particulate matters, which means unburned carbon, is concerned, we have actual elimination of particulate matters in the case of dual fuel. As far as the pilot fuel is only 1 to 3% of the total amount of fuel, and here 20 or 40% decrease in the case of particulate matter in the case of gas diesel engines. So if we see the operating points as far as NOx is concerned, so gas diesel engines comply with Type 2. Gas dual fuel engines with premixed combustion can comply with Type 3. In conclusion, additional measures are required in the case of gas diesel engines after some years when the Type 3 level will come into effect. And as we discussed, there are only two ways: is that either SCR, NGR, or a combination of these two.
Excuse me.
Yes.
Can I see the previous slide?
Yes, of course.
The upper one is based on the MAN BMW energy engines.
Both are taken from Wärtsilä. Yeah. Because Wärtsilä
Yes.
Has been producing gas diesel engine 20 years ago.
Yes.
Apart from shipping applications or marine applications, power plant applications are extensively used. So dual fuel engines and gas diesel engines have been used in the past, or have been extensively used in the power plants.
Is both one as the based on four-stroke engines? Or?
Yes, four-stroke engines. Four-stroke engines.
I have some understanding problems. As far as I know, the Wärtsilä dual fuel engine system adopted the four-stroke engine for the auto cycle, but on the other hand, the MAN BMW using the diesel cycle of adopting two-stroke engine for dual fuel system.
Correct.
So the Wärtsilä engines, as you discussed it before, that's why the chamber temperature and pressure is relatively low. It meets the current regulations. But MAN BMW engine inevitably used a very high pressure injection fluid.
Yes.
So that is unable to meet the Tier 3, right? But now you said the Wärtsilä engine using two-stroke engine.
No. I said that both. Wärtsilä engine.
Yes. Yes, but they still use the low pressure compared to MAN BMW. MAN BMW engine used the up to 300 bar for injecting the fuel, but in your slide, the Wärtsilä's two-stroke engine use only 10 bar.
Correct.
So is there the performance differences or?
Yes, I mentioned that. That there is a decrease of delivered power.
Correct. So the two-stroke engine of Wärtsilä is the performance is similar to four-stroke engines of dual fuel and.
Just a moment. As I mentioned, we need to consider which are the basic types of engines. We have two different combustion concepts: premixed, diffusive.
Yes.
We have two different cycles: two-stroke, four-stroke.
Yes.
We have two different concepts: diesel, auto,
Yes.
We have two different injection concepts,
Yes.
port
Yes.
injection,
Yes.
in-cylinder injection, and then by taking into account all these, four-stroke gas diesels means that the gas is injected within the combustion chamber. This is four-stroke. I've taken from a Wärtsilä presentation, so it's four-stroke Wärtsilä engines of gas diesel type. This is Wärtsilä again, four-stroke dual fuel engine. So we need always to know which is the type of engine that we are talking about. Certainly different types of engines present different advantages and disadvantages.
Have we got any performance data from the two-stroke, newly developed two-stroke engine?
All these data are available on the sites of Wärtsilä and MN. So if you go there, you will find everything. So all the data are published.
Thank you.
So my last two slides for had two slides. Probably I didn't. Anyway, I have the last slide for this session. Okay. So as far as we conclude in the engine selection, in the engine type, in the concept type, combustion concept type, then we need to take care the onboard storage and feeding system, because gas or natural gas needs to be injected. It needs to be provided and injected to the engine. So in this case, this is a concept from for four-stroke engine, and actually this slide provides the storage and feeding system. Certainly in the engine, natural gas in gaseous form will be injected, and usually ambient temperature, something like that. But then there is another problem. In which form the fuel will be stored? Will be stored in liquid form? Will be stored in gaseous form? Now we have the selection issue between LNG and compressed gas. Why LNG is preferred? While liquefied natural gas is preferred instead of compressed gas. We could use compressed gas to avoid the very low temperatures of minus 163 degrees Celsius. I think you must have covered this part from other lectures. So why LNG is preferred?
Because it's higher density, so we need the lower space in order to store it.
Exactly. So in this case, LNG provides the benefit of lower or limited storage space required, but we need to keep the LNG in very low temperature, and of course we need to provide gaseous natural gas in gaseous form in the engine, and then a number of machinery components, piping system, safety measures need to be taken into account in order to have this system on board the ship. The main components, I don't know if you covered in other lectures this topic, but just shortly to mention that the basic components used are, of course, the storage tank, and then we have heat exchanger. Actually, this is a glycol water heat exchanger. So we have on the one hand LNG, and the other hand a glycol water mixture. Gas valve unit. This is a safety measure, safety component. There is a pump, but there are systems without a pump. So in this case, a couple of alternatives have been proposed, and Of course, we need to have in mind that storage and feeding system. So we need to store the fuel amount required for specific voyage or specific period of ship operation, and also we need to feed natural gas to gaseous form of the engine. So there is a huge discussion, and there are many selection options how to select the best combination of components. So I conclude here with this slide. In the afternoon presentation, I have an example, giant example of an open type ferry taken from a project that I coordinate called LNG Comship, with the objective of converting an open type ferry from diesel mode to dual fuel mode. So we can discuss in the next session in detail all the different aspects of storage and feeding system. And of course, we need to take into account the safety requirements, classification site requirements, double wall piping is required, ventilation between the piping is required. We need to avoid issues from natural gas leakages or LNG leakages, which are very dangerous. But research is in progress, and the manufacturers, I think, see that the application of LNG as first priority. I also heard that Japanese government put that also as first priority for Japanese ports. So there is huge ongoing discussion and the future on the application of LNG on board ships. So if you have, I think, 1-2 minutes, if there are any questions, I can have to answer. Yes?
You show us some diagrams with permissible limits of emissions.
Permissible, or you mean the NOx, the tire IMO levels?
Yes, I think. There was some curves with level of emission.
These IMO levels.
Yes. Why the level for the low speed engine are is higher than the other for the high speed engine?
It's a good question. Just to clarify something which possibly is not clear. The emission level is grammar per kilowatt hour. This does not mean that the engine will emit less amount of NOx because the amount of NOx emitted depends on the engine power. So you have an engine with, let's say, 10 megawatts power, and you need to multiply this factor times the power of the engine. So actually, this is specific emissions, NOx emissions in grams per kilowatt hour. Now, the reason actually is comes from the fuels used by the two-stroke engines, heavy fuel oil. Heavy fuel oil is a very low quality fuel. So you expect that the engine should emit more or higher emission, higher NOx levels. But this is, as I said, this is grams per kilowatt hour. It's not the absolute emission. I have an Excel file that we can discuss it in the afternoon session as well, which is used to calculate emission levels and emitted amount of constituents, depending on also on the power of them. So we need to know that the absolute amount or the emitted amount of NOx will be calculated by using the power as well. So it's grams per kilowatt hour times kilowatt gives the grammar per hour, the mass flow rate of NOx.
Yes, that means that if I have a ship with one big two-stroke engine and another with two high-speed four-stroke engines, the regulations for the first ship
Yeah, depends on the speed.
are more flexible.
Depends on the speed. No, they are not flexible. Depends on the speed of the engine speed. Always the regulation, as far as NOx the emissions are concerned, the regulation depends on the engine speed, the rated engine speed. So all the merchant ships operate with two-stroke engine below 150 RPM, so there is no differentiation here. Then depends on the engine speed, but we need to remember that the highest the engine speed, the lowest efficiency.
Yes.
So, but this is another discussion. Any other question?
We can see if we have any questions.
Yes.
Because I saw a raised hand.
Could be. Pilot fuel is liquid, certainly is liquid. The question is if pilot fuel is heavy fuel oil. Certainly, pilot fuel is liquid oil, liquid fuel. So usually marine gas oil or marine diesel oil is used, or low sulfur marine gas oil is used within ECA exhaust gas emission areas. Exhaust control areas, but yeah, heavy fuel can be used as pilot fuel.
Okay. Is there any other question from Spontanea? From here?
So we can conclude this session.
Okay. We will have the 30 minutes break, and afterwards we will continue.
So thank you very much for your attention.